Okay. So let's get started. Sorry for the delay. It was missing keys. So last time we finished unsupervised learning. Like we learned two major problems. One is clustering, and another one is dimensional reduction. And today we are going to learn supervised learning. And the most easiest way to learn supervised learning is by doing the simplest method, which is linear regression. And this linear regression actually is something that you learn in high school, but they don't tell you that it's linear regression. They tell you it's something else, but it's essentially what you have learned in high school. So we want to kind of like relearn it a little bit, and we want to formalize the method for generalized ideas. Okay, so we start with the motivation. So why do we need to learn linear regression? So every method, right, every problem comes from like a real world example. And so what do we have here? I have a plot, right? I have like these 6 data points, a plot between BMI, with like body mass index and blood pressure. And what do you see on the right? In a scatter plot, what can you tell about data? Right? So we have like 6 data points. Right? We have like 6 data points. Right? 1, 2, 3, 4, 5, 6. So what can you tell about this data? Right? So as the BMI increases, the blood pressure also increases, right? So that is like immediate thought when we see this kind of data. So what we actually want to learn from this data is a relationship, right? When you put something together, you expect there must be some relationship between these two variables. So we kind of want to, establish a relationship between BMI and blood pressure. And in the future, maybe we could predict the blood pressure from BMI. So what do we need in order to predict the blood pressure from BMI? Right? If I just give you 6 data points and then ask you, okay, my BMI is maybe 31. What should be my blood pressure? So it's about this way, right? Right? It's about this way. So there are many ways that you can predict. Right? From the data point, if you have the data with 31 BMI, you must answer that data. But if you don't have 31 in your data set, you can do something like interpolation, right? So maybe this one is like 36, about 36, and it's 140, right? So we have from 30 to 36, and you go from 130 to 140. So 31 is somewhere between them. So you can interpolate the data. That's one way that you can do the prediction, right? But we want something more, right? We want something more generalized, more helpful. We need a model. We need a model to actually describe the data as best as we can. So it's not just interpolation, right? We want a function that can map the input to the target. So the relationship, we want it really compact, right? Why do we want it to be compact? Because in the application, right, when we want to predict something, you don't want to spend a lot of time, right? So a lot of reasons, right, is done via training. But the evaluation should be very quick. Because when you want to use this model in the real world, you want it to be verified, right? For example, you have face detection, right? You develop a camera app, and you want the camera app to automatically capture to see which face in the image, so you can focus on your face more than the background, right? So the algorithm to detect the face is really fast, but the algorithm that is implemented before you can actually detect is really slow. So we want the relationship to be compact. So by compact, right, I want less variable, right? So if we want to explain the relationship, I need to have some information, right? Maybe it is a line. How can I describe a line? What do I need? What is the minimum thing that I need to describe a line? So you would have like slope and then intercept, right? So there are two variables, right? So if we have like linear data, and then you can just summarize this linear data into two variables. That's right. So the linear function is easy to understand, right? That's why we pick linear function. Of course, there are more functions that we can use, right? There are like quadratic, there are like what else? Cubic, right? Polynomial, maybe log, maybe exponential, right? So there are many functions of them that maybe you can explain the data. But we want to focus on linear. Why? Right? What is the most simplest thing? Right? It's easier to explain in linear. And most of the time, if you want to try like a more sophisticated method or more sophisticated function, it might be better to transform your system, right? For example, if the true model, the correct model, right? Maybe like so this is y, this is x. Perhaps the true model would be like y equal to like e to the x, right? And when you model this, right, you would have maybe like a e to the x plus b, right? So they are still like two variable, or sometimes they are like third variable, they are like this, huh? Right? And to learn this function is not quite easy. But if you can transform, right? Maybe you take the log of y and x, and suddenly the relationship between log y and x becomes linear. Right? So sometimes it is easier to just transform your figure. Take the log, or maybe square it if you want to do quadratic function, or you can just multiply the figure together. Right? So there are many ways that you can deal with the figure so that you end up with a linear relationship. Right? So if linear relationship doesn't explain your data very well, then you can try transforming your feature. So what are the challenges, right? So there can be many lines that you can fit data, right? I have like these 4 lines. Which one do you think is the best? 1 through 4. Which one? 1 through 4 or 2? Okay, someone say red. This is the line number 1. Okay. Why red is the no? No. So you have red and red. What is the difference between red and orange? So the orange line has to like almost 2 points, right? And then with the red line, only near 1 point. One. Right. So when you say something is better, you have to give some mathematical explanation, give some mathematical value. And what we actually discuss right now is we actually look at the residue. What is the residue? The residue is the difference between the point and the line, right? It's the distance from the point to the line. And when you look at the big picture, you want a line that are closest to every point in the data, right? As close as you can. So to pick the baseline, you have to come up with some measurement to basically give a score to a line. I give you maybe like I give you like maybe like 1x plus 2, and then we have like 1.1x plus 1.5, right? So I have like 2 lines right here, and you need to have some function that transform this into some score, right? Maybe this will give like 0.5 score, this will give 0.4 score, and then you pick the best score, right? Or something. So we need a way to score it, and we actually have some idea, right? The distance between right? And now we come to the regression, right? The task that we're doing right now, right? Because we want to find the line that are closest to every point, which means that the point itself is actually our data. So we have a graph here, right? We have something that we can, and so because we have target, the task is called supervisor. So whenever you have a target, you have the answer, you have the correct answer. So that when you evaluate the model, you have something to compare to. Right? When you have a comparison, then these are supervisors. And regression analysis is a study, right? A study of method that you look at the relationship between the input figure and the target. So today we are looking at maybe just one variable, but it can be extended to many variables. And we also focus on the linear relationship. So let's start with some formulation, right? So we have our data set, right? X1, Y1, right? So for our example, right? So we have X1 and then sensitivity Y1. And we want to find a real function fx such that the distance from the point and the line would be small, right? So this is actually a Euclidean distance. right? I took it in distance. But because y only have one variable, right? We have one. So you don't have to do some things. So basically you just so yi is the ground truth, right? And then this one is the prediction. Right? You put x into the function, and then you get a prediction. So the difference between the ground truth, the correct answer, and the prediction, that would be the distance from the point to the. And what do we want to say? Normally, when we look at the distance, right, you can just put the absolute value, right? You can just put the absolute value. But the problem with absolute value is that it's very hard to differentiate, right? So if you have just square, then you have like this curve, right? But if it so this x square and then this is like x. So for absolute x, I think this point is like non-differentiable. So when your prediction is very close to the graph root, then everything will become true. So that's why we take the square, right? And then you sum up all the points. And basically we want that minimum with expression become optimization. And this optimization problem, you actually learn in high school, right? When you have a bunch of two variables, you sum it up, and then you square it, and then you sum it up, and then you can solve the equation. But for us, right, we want to find a linear function, right? So for a linear function, we have a function of this form, ax plus b. Right? So a is non-variable, a is a parameter, b is also a parameter, right? So a is basically a zero, right? And then b is intercept. So the SSR that we have for, right? So we want to find the minimum of A and B, right, of SSR. And basically we want to find the minimum. And we will see later how can we reach the minimum. Now, apart from SSR, we can use correlation. We can use correlation is another method to measure the extent of the association. Because when we use SSR, right, it's going to be one answer, right? One answer. And when you get the answer, right, you get A and B, and then you want to convince someone that is the best A and B. So there are measurements that you can convince. One would be correlation. So the correlation, it would take value from -1 to +1. And 0 means that there is no relation between these two values. Basically, it's just random. If it's -1, it means that it's perfect negative correlation. And so you like all the data is on this line. It's like perfect. And the positive would be on this diagram. So if we have the correlation value, right, we can measure the strength whether or not two variables are actually related, right? Because here we can get A and B, but what people want is accuracy. How good is your prediction, right? And how good is your prediction can be measured by correlation. How can we compute correlation? So let's start with example. So our own, if you want to guess what is the correlation value for BMI by network, what is 20? Right? Someone said B, right? Why is it B? What is it? It's positive, right? So you can move up all the negative. Now, in the positive, you have 5.1. But 1.5 is not possible. The correlation is from 1 to 1. So you have 1.5 and 0.1. And if you look at the line and the data, you would think that it explains the data very well. And if you think that it explains the data very well, you will have the higher correlation. What about this one? Now you come, now I don't want to anyone to give you data. So I have the percent in the hormone, the percent and percent in the. What is the best guess? Actually, what should be the one? A, why A? If you were to draw a line, where would you draw it? Right? It's going to be positive or negative. If you want to draw a line. Right? You want to line something like that may be something like this. Positive. And then right? Because like between positive and negative, you would think it's more positive right, than negative. So this is your original answer. If I don't use this, would this still make sense? So basically, there are some point right along this line, right? These are some point, maybe this line, that can be explained using this line, right? Using this line. But there are something outside, right? Like this outside that cannot be explained. And if you look at it like this, basically you will get something like this. So you can see the positive, but it's not really strong because there are some points that are far apart from the line, but there are also some points that are close, right? So that is what the intuition should do, right? It's not negative because most of the point line is the positive relation. Right? If you want to draw a line for the negative relation, it doesn't make sense. So which of the following has the strongest correlation? So socket here means like it can be the most negative or most positive. What do you think would be, which one would be the socket? B? So someone say B. Between A and B, right? Here, if you look at the top, here, the bottom. On the top, the point are actually forming a line, right? Forming some kind of line. But on the bottom, it's spread out. Right? So that should immediately tell you that top should have proper correlation there with bottom. Now, between A and B, why do you pick B and not A? Is linear, right? So correlation, the definition of correlation only care about. So if you were to draw a linear line for A, right? Perhaps you can draw something here, and then you get most of the line, but there are something else, right? But for B, if you draw the line, most of the points are actually agreeing with you. So the one hand, the strongest correlation would be as your input. Yeah, so for A, it's like mostly would be like some kind of like square. So if you take like the square root of y with x, perhaps you might get solve. So to find A and B, we have one method. And this method is called leading one. So what does this method do? So what we talked about earlier is value, right? It's basically is the leftover from the model field, right? So you have your model with the left, and then you measure the difference from the line to the point, right? And so we can just write the relationship, right, to be like the data equal to the fit, basically the red line, plus the green line, which the fit. And we want to focus on this residue, right? So we have yi, and then the predicted right-hand line. And we define for each data point, we have the residue. It's basically just subtract the ground truth with the prediction. And what we want to do, we want to find the baseline. So the baseline, we want small residue. We want the small residue. So there are many options that you can do minimization, right? You can just absolute value of each term. And then the also option 2 would be take the square of each of the error and then you pick option 2. But why we pick option 2 over option 1? What do you think are the reasons that we pick option 2? So, well, the first reason is the most commonly used. People just intuitively use the sum of square error. And this one is easier to compute by hand and by a computer And the last one is, if you think about it, right? If the residue is twice large, residue is actually twice more than twice, right? It's not the linear relationship. Because like if you, let's say you try to get enough, right? And then you are off by two, and our friend gets the same number but off by four. So the difference is twice, but we are actually not focused, right? So basically, like you have the line and you have the point that are twice as long. We want to penalize. We want to penalize the profit right more than the profit. Because we want to capture order. That's why you want to penalize the point that are far away more than the point that are. So when you do the optimization for these expressions, the term that you dominate would be the one that are furthest from the mean, right? Because if it's close by, when you take the square, it's going to be the mean. But if it's very far away, when you square, it's going to be very mean, and it's going to dominate. So what this implies is actually not to minimize the impact of the country, the furthest. And you compare this line to the point that are farthest away. And the baseline would be the line that furthest point is the closest among any line. But for here, this is our first intuition. Right? We just want a line that are close to every point. Right? If you think of the line that goes to every point, then it's the option. But if you want a line that the furthest point is the closest point, then that's option two. Right? So if I have like two lines, right? If we have two lines, and I have the furthest, right? This one is far away from the two lines. Then I want to pick this line with the closest one, even though the point in between change a little bit. Right? So this one comes with one, right? So the point, what's the bad thing about using this expression? You want a line that the furthest point is the closest. What can go wrong? What do you think can go wrong? What would the impact? The minimization very bad. Something that starts with O. And the word that you to mind, it is not important. Something that will make this method look little bit. O, U. Ring a bell? Any word? It is outlier. What is outlier? It's basically output, right? Right? If I have like this line if let's say I have this data point B, and then I just have one single point here. Now, if I have one single point here, this is outlier, right? But if we don't know that it's outlier, and then we use everything, then maybe outlier would be like on the bottom side of the order point. But if we remove the outlier, then we will get like a better line that go to every point. So when you see something square, right, you are immediately thought like the outlier is going to go, right? It's going to make this expression really large. And when you want to minimize it, you see that the model is going to care too much about the outlier. So that is one thing that you have to keep in mind when you do that it's really broad. Now I'm going to show you just one variable. What if we have more? What if we have more? We want to write it in a general form, basically in metric form. So we used to have ax plus b, right? Y equal to ax plus b. That's our linear function. But when you have more than one variable, right? Of course, you want to have more than one variable as to input feature, right? For example, you have image, right? Image will have to be like 1 million pixels, so you have like 1 million pixels at least. And therefore, you have to generalize the idea, right? So we can write our equation using xa equal to 1. So x is the data matrix, right? X is the data matrix. So if our data, right, we have maybe like feature 1, feature 2, and then we have the target, right? All these number here is going to form an X. Right? So that's going to be your data matrix. And Y would be just the target. And so what is here is basically the parameter of the model. In our case, we used to have A and B, right? We used to have A and B. So how many variables do we need for A? Right? So this A is to be a vector. It's going to be a vector for parameters. Right? So for each of the feature column, it's going to have its own slope. Right? It's going to have the slope of S1, slope of S2. So, but our data have S1 and S2. But when I write the metric column, one will have to be one. One way put one element. And why are there A2? Now you think A1 is for S1, A2 is for S2. What is A3 for? Right? So there are two questions, right? Why this one is O1? And then why, what is A3? Intersection. Right? So it's basically B in our origin. Right? But when we write, right, so we have x1, x2, x3, then we're going to have the a1 plus a2 plus a3, and then we pass an or a plus 1. Basically, you have the intercept. Now, this intercept is for every column. We don't have intercept for each of the point because essentially it's going to sum up to 100. And why do we fill with 1? Because when we do multiplication, right, this 1 is going to multiply by this, so you can get the 80. Right, so that would be this. And then these two columns together, 3n1, 2n2, and so on. So we want to find A, right? We want to find A. If we just use our metrics knowledge, right? We have x A equal to y. We can just multiply x inverse on both sides, right? And then you get A x inverse y. Right? That would be perfect. But why I cannot do that? Why I cannot just multiply by x inverse? The reason that I cannot divide by x inverse is because I cannot compute, right? Because when you think about the inverse, right? You think about inverse. What is the condition for inverse? To be able to find the inverse, what is it? You should remember from the inverse. Basically, there are two conditions. The first condition is the metric has to be 1. The second condition is the rank cannot be zero. Basically, the determinant of the metric cannot be zero. And which condition that we want? Basically, 1. The first one. Why? Well, in this example, it happens to be 3 by 3. But in general, what is the size of this metric? What is the size? Right? So you have, let's say if your data have m dimensions, and then you have n data set, you would have n by n. Right? You will have n by n metric. And most of the time, you have more data than you have. Right? You have 1 million data, but you have like maybe a half of it. So the metric in the market are going to be. And to compute an inverse for a really large metric is convolutional intensity. You know what to compute inverse? You never compute inverse using a computer because it's going to take a long. So if we cannot find inverse, what should we do? We do. We don't know what to do. So in the least square, right, we want to find the line with the smallest residue, right? And we use L2 norm, right? We use L2 norm, right? Because before, when we define the error, right, we like yi minus y hat I and then square, right? So the target, that's for one data point. But here we think of it of the metric. We think of it of the entire data. So one is actually, and when you minus, when you compute the residue of the entire data, basically you just use the L2 norm, right? It's the same equation, but written in the metric form, right? And the L2 norm is basically A transpose. So basically, you're gonna have like y1 minus y hat 1, y2 minus y hat 2, and so on. And then when we do the transposition, right? The transposition, you would have y1 minus y hat 1, y2 minus y hat 2, and so on, right? And then when you multiply these two metrics, right, this one you're going to multiply. So what do you get? You get y1 minus y hat 1. Right. So it is the same formula that we have before, but we just write it in the metric form. And this function, right, when you use L2 norm, the function for the L2 norm is convex, right? The convex function is the function that all the boundaries will form a polygon. So something like this, like, is a convex. But if you draw it something like this part is not convex, because when you go from one point to another, it's actually outside the one. But when you go from two points, the distance between 2 points inside the convex would be the same. Would be inside the volume. We'll talk about the condition later, but for now, this function, right? This L2 norm function is a convex function, and the problem of a convex function is have global. So when we have a function that has a global minimum, how can we find the global minimum? I can give you a function. I told you that this function has a global minimum. How will you find it? Well, you can use output, right? So when a function has a global minimum, the global minimum will occur at critical point. And the critical point is the point where the derivative at that point becomes zero. So we can just take partial derivative of L with respect to A, and then we set it to zero. Okay, let's try. So what is our L? Our L is this one, right? So we start at xa minus y, right? So we want to find the partial derivative of this. How do we take the derivative of the L2 function? Well, we can write this in the metric form, right? So we know this formula. So we use this formula to transform this into something that we can make a derivative, right? So this one is going to equal to x a minus y transpose times x a minus 1. And then we distribute the transport into the benefit. What do I get? If I distribute the the transport. Oh, this one is the same. What about it? So we have, okay, this one, right? This is one transport. What about the front? Right? So XA transport equal to, so which one? This one or this one? Which one? Right? How can we check which one is correct? We can check the right? So our X is n by n, right? In row and column. Our A is n by 1, right? In row, 1 column. So X times A, how many columns? So we will have n times 1, right? Right? Then in row, 1 column. What about XA transport? We're going to have 1 times n. Okay? So we have X transport, A transport. X transport, how many row, how many column? It's going to be M times N, right? So see, you flip over column, right? And then A transport, you get 1 times N. So our target would be 1 times N, right? That is the target. So which one of these give me 1 times N? 1 or 2? 2, right? What 1? What I will get? If we do 1, I get basically I cannot do 1 because the dimension doesn't match, right? I can only do 2, right? So this one you get A transpose times X transpose. So when you distribute the transpose to the multiplication, the order is same. Right? You can check your matrix property. You follow to stop here to here. Right? You can check the addition. Right? And this is the only way that you can do. So when you have to distribute the transpose, the order is not additional transpose. And then we just multiply out these two, right? We multiply out these two. What do we get? So I get A transpose X transpose XA, right? So the first term comes the first term, and then we have minus Y transpose XA. And then we multiply this into the end, right? So we have to be minus, right? And then we have minus A transpose X transpose Y, and then plus Y transpose Y. So that's our function. Now we can take partial derivative for each term. What do you get for the first term? Okay, we can skip. What is the second term? So basically A is just power one. So this one you get just y transpose x, right? This one you get, you take the derivative, right? You get x transpose y, and then this one is a constant because there's no A, so it becomes 0. What about the first one? So if you have A in the front, right, and A in the back, how would you take the derivative of this one? Right? So when you don't remember the to calculate, you can ask a website. Right? You can ask a website. And the website that you can ask for math is called Wolfram Alpha. Have you heard of this website before? Wolfram Alpha. This one. Right. And then you can ask the calculus, right? You can ask the calculus, right? It's gonna tell you to do the derivative, right? For example, if you put the equation here, right? The derivative of x of this form, right? It's gonna calculate it. So we can do what we can do is like, so we have a transpose x transpose x a, right? And then we want this we have to put the parentheses, right? I think we have to tell it that it's a matrix because otherwise thought that is to the power of t, right? So let me try where x is the matrix. It is. Let's see if we can solve. I actually haven't tried it. So basically, it doesn't interpret this as symmetry. So what I say, like vector calculus, maybe it will have some function that I can. Oh, there's a gradient. But it doesn't have the metric. Right? Let's see. So it's only deal with just one way. So we can add Gemini. Can we ask ChatGPT to do for us? I want to find. Now my student have to log in, right? Okay. Or maybe someone try. Do you have Gemini or ChatGPT on your phone? I want to see if it can take the partial derivative. So what did you get? You get anything from ChatGPT? What are you saying for this term? So it's basically treat like it basically treat this as like a coefficient, and A transpose A you get to be like A squared. And so basically this becomes like A transpose X times A squared. And when you take the partial derivative, you get 2x A. So did you get this? Okay. Okay. Anyone has any other than ChatGPT? You get it's basically first product function. So you take the power to the part and then you reduce the dimension by with the exponent by one. So that's why it's two. And then we set this equal to 0, right? And then what you get is you get x transpose x a equal to for this two part y transpose x minus x transpose y. This actually because the a here is in the opposite direction, right? In the outline and below. Actually, when you take the derivative in the transport, you actually transport this one, right? So this one it actually become the same, right? You get y transport x just because the a here is the transport. And then you have this one equal to 2y transpose x. And then you can solve it to be um, actually, yeah, just had to be one. Actually, you have this one like this before doing. So you have the gradient. You have the gradient. You can solve this because when you do x transpose x, right? When you do x transpose x, your matrix, this one is going to be square matrix. And because it becomes square matrix, you can let's multiply the inverse of it on both sides. And then you let it on one side, and then you get the solution on the other. So for the closed form, right? For the closed form, right? You get x transpose x a equal to 2y transpose x, right? The two cancel out, and then this one you can multiply by the inverse. Right? And then this one just becomes, right? Because the inverse time itself will become identity matrix. So this is the closed form solution for the linear regression. But to compute the inverse of this matrix, right? So this metric is very large, can be very large. And when you compute the inverse, right? And sometimes, right, the determinant might be zero as well. We don't know. So if the determinant becomes zero, then it means we must get the inverse. So even though we have the transform solution, we actually don't use the transform solution in the application. So what we do, we actually use this gradient, right? We kind of use this gradient as the upgrade, the update function. So basically, we have our A, right? We have A. We find the gradient, right? We find the gradient, right? So that's called triangle. And then you can update with the learning rate times the gradient. So what we do we use the gradient descent or the Newton method, right? Basically, you have some kind of a function that you don't know, but we know that it is convex and it has the probability. So you just take a guess, right? You take a guess, you compute the gradient, and then you just move the point into the gradient. Because when you have a global minimum, the left side you have the negative gradient, on the right side you have the positive gradient, and when you reach the global minimum, the gradient will become zero. So if you calculate the gradient, then you move into the right side, so that your gradient will become smaller. And to become zero, then you actually find the global minimum. So this is the gradient descent method. So when we take the derivative, when we be calculating the gradient, is the direction. It will tell you the direction to the global minimum. And we just move to that location. And we cannot just move normally. Normally we will have what is called the learning rate. Basically, the step you take, right? Because if you take too far the step, you might miss the global minimum. Right? For example, if I have the global minimum right here, right? My current point is right here. I compute the gradient and I move very far. I would go over, right? And then if I move back again, but it's still very far, you will get past the global minimum. So the learning rate here is will change over time. It will start out very large, and the step will become very small as you get closer to the global minimum. And you will see this learning rate later on. If we do auto learning, it's the most common parameter that you will see. Right? So that is how we solve the least square solution. Right? You can find the limit and then you update your A with this formula to get closer to the global minimum. So what is the condition for the least square? Right? So to be able to use least square for the data must follow a set of conditions. The first condition is linearity, right? So there is the linearity between the different targets to be linear. It's not just for all the figures. Each individual figure have to somehow have a linear relationship between that figure, right? So we have like F1, F2, F3, and then we have the target T. When you plot F1 with T, F2 with T, F3 with T, each of the graph that you plot should have a linear relationship. So how can we check that the plot has a linear relationship? For each of the one variable. So we can check by plotting. Right? We can check by plotting. Now, there are two plots that you can plot. The first part is actually your data. Right? So you have the target here, and then you have maybe F1, F2, F3, right? So in this case, you can see that F1, you have the linear relationship, F2 has linear relationship, F3 does not really have linear relationship. And what do you do before you perform the linear relationship? So you don't have to use all of your figures when you perform linear regression, because you want to make sure that these features that you try to fit the model actually have a linear relationship between that feature and that. So we can just remove F3 and then just do L1 and F2 for linear regression. Another point is the bottom one. The bottom one is residue. So what is the residue point? It's basically you have the economic line, right? You plot the difference of each point to the line, right? So if you have the residue, and then the bottom one is still going to be F1. And if the relationship is linear, all of the point, all the residue should be very positive. It should be very positive. So if there are points that are far away from zero, then it's an indication that both is not going to work because it doesn't have linear relation. The second condition that we can check is normal residue. Now, I told you that the residue should be 1 to 0, right? Across time. But there are more too. Not just close to 0, but if you plot the histogram of the residue, it should follow the velocity or normal distribution. So what does it mean, right? It means that most of the points, right? Most of the points should have a residue 0, 1 to 0, maybe some point outside the range, and the histogram plot, it should follow the normal distribution. So this should be very easy to do the residue plot. So that is the second condition. Right? So not only that, it should be equal to 0, but there's a way to measure how close to 0 to based on the distribution. Right? There's no model that can fit every data, but majority of the data should be explained. The third one is for homoscedasticity. And this is actually the variation of the point along the line should be roughly constant. So what do I mean by that? Right? It means that as you move along the line, right? As you move along the line, the density, right? The density of the residue should be roughly constant. And the case that is not constant is something like this. Right? You have this side has the residue very close, but this one has the residue far apart. So for this case, you can check with the histogram plot or the normal probability plot of the residue. So the variety of the residue around 0 line, basically if you do the residue plot, right? And then you take one shot, the distribution of the residue should be roughly the same. So every shot of the data that you okay, so which one this? Which one of the condition is violated? Right, so that is violated the first one. Is the relationship linear? Well, it's not really linear. Right? You go here and then kind of go down. Right? So this one is not. What about the normal residue? Right? So if you look at the residue part, thus the residue. So if you take like this band, so basically most of the points are near 0. And then some are outside, right? Some are outside. So this one is low, right? Because you can kind of want to this to have like a tail curve. Like most of the points are equal to 0, and then maybe some of the points are in the tail of the one. What about homozygous? So for the homozygosity, right? You look at uh, the distribution over time, over the world, right? So maybe you take this area into 4, and then you look at the distribution of each one, right? So the first one, distribution would be something like here. The second one would be like very large, and then this one would be like over on this side, and then the last one would be on. So the distribution of each of the block is actually different, right? It's actually different. So this one is not. What about this one? This one of this is well then. So it's linear. Yeah, it's linear, right? If the residue follow the normal distribution, right? So if you look at the whole picture, right? Then you would get a bell curve. If I just sum it up, yeah, you should get a bell curve. What about what's that? So this one is the estimate for variability was that because as you go, right? So at the beginning, all the point are really close to the line, but at the end, the point are further, right? So the variety change when the value of the feature change, right? For F1, for the low F1, you can explain it. That's how we know. But for high F1, you can explain it. So this one does not follow almost nothing. So you can just modify the feature like this, then you can just follow it. Right? Not use it if the area is. So as you can see, there are actually a lot of assumptions in order to be able to put this graph for the data. Right? But simply just one that can explain our data. So we have the method, right? We have the method. When you recall, right? When you recall that, okay, this line explains my data. You need a little bit more evidence than just saying that this line explains the data. You need some confidence there, right? How confident you are that this line actually explains the data. How can you find the confidence? So we have R-square. Have you heard of the R-square? Maybe some of you have. We thought that it is. And R-square measures the extent of the fit of the linear volume. Right? R-square is the square of the coordination coefficient. Right? This term is from statistics. So you can look at this term in statistics. But what it tells us, right? What square tells us is the percentage of the data that can be explained by the data, right? For example, if I have R square, let's say I have my line, I have R square equal to what does y x? This y x means that 80% of our data can be explained using this one. And the other 20% also. The rest of the 20% is just random guess to perform. So as well is actually very good metric, very good value when you want to report your spread of the data. Like for a linear model. Right? So R square only work for the linear model. So the formula for R square is quite different. It's 1 minus SSR over SST. We already have SSR. This is the sub-square residue. Right? This one we already have. Basically, you take the prediction and the graph rule, right? You subtract it, and then you square, then you sum. That is it. What is SST? SST is total sum of, and what it does is that, well, why am I? Why? What is why? Why is the average of all of them. So you have your target, right? You have your target. You just compute the average of all the targets. That is your y-hat, right? So basically your y-hat is like sum of the yi divided by n. So this is basically this one is the score between the data you put in. This one is the score between your data and the average. What is the average? Basically, this is like rate of guess, right? And when you do the rate of guess, you just take the average. Right? For example, if you know that the answer is between 1 and 10, you just take again or 5. Right? So when you compare your model to the chain, to random chain, right? So if your model is good, right? If your model is good, this one is very low. Basically, this one is constant, right? This one is constant because this one only uses data. But the top one, the y-hat is from the model. Right? You have the target. So if you have many, you can just compute the graph of each line, and then you compute R square. And then will tell you the strength of the model. So you want the R square to be now interpretation of R square. Right? So R square will be from 0 to 1. From 0 to 1. 1 means perfect fit. In that like every data you get R square. If R square equal to 0, it means that it's better to just take a random guess than use your model. Right? That's defined by R square. So R square of 0.38, that can be that 38 of the data can be obtained by this linear. And we talk a little bit about outlier. For least square method, outlier is the word anyway. Because it can strongly impact the performance of the least square method. Right? Because the least square method you quantify the line that the 30th point is the 40th. Therefore, you have this data, and then you have this outlier. And if you use this outlier in your data set, you will get the dashed line. So the dashed line is the line that you get with the data plus outlier. But the red line is the predict line that is the outlier. And the red line actually extends along the data set that is that. So we need to find where to find. How can we find online? Yeah, it's the most common, but it doesn't have one method that can do algebra. Right? We can use uh clustering method, right? We can use math, for example, the point that have low density will be higher, so that can compare to it. We can use clustering. Maybe if the point is too far, maybe you can pick up it's too far for the cluster system, maybe it becomes young. So it will depend on the data. There are many ways to now use by the outlier and then know what method I can follow. So that is all for the linear right? So we will learn one method, but to get to that method, we actually have a lot of steps. And we're going to take a 5-minute break, and then when we come back, I will explain the excitement. You also have only have the announcement for the technical component, but I will explain for those of you who have never tried the technical. So we'll come back at 10:50. Okay. So if you go to the assignment in the Mango Canva website, it's going to be a link, inviting to this Kaggle commission. So I create this Kaggle commission with the name assignment 1 for our course. And the goal of this assignment is for you to develop regression to predict the yield of the Y tuber. So let's look at the data. If you go over to the data set, I have explained to you what are the so I have put the explanation of each of the column. So I think we have about 18, 19 columns, right? And then we have this all the feature. And our target would be this column U would be the target that we want to predict. And the file that I have is train.csv, test.csv, and then sample submission.csv. So for the train CSV, you can download offline. For the train, the train CSV is going to be your data for training. Basically, it have all the feature plus the target. Right? So I want you to predict this column using the value of the rest. So the train will have everything, and in the test data, is going to have all the column except the U. So basically, you have all information except the correct answer, right? And your job is to produce the submission file. The submission file is going to have the ID and the target. This ID must match the one in the test. So this ID, basically your answer is going to have this ID of the test, and then you have the second column would be you. So you have two columns for your submission. So here, you only need to submit the prediction. You don't have to submit it. Basically, you can create any model, and you can click submit prediction. Basically, you upload the file. Let me know for submission. So the submission, it will look something like this. Right? You have the ID and then the yield. Right now, my yield, I just use the average. I compute the average of the yield and then just put all the bridge. So if I click submit prediction, I can upload my file here. For example, I upload my sample submission, right? And then you can type the description. It's better for you to type the description for you know which submission you want to have, because you can submit any answer. You can submit any answer, and then you want to make sure that this answer corresponds to this module, you can name your model the best thought on so maybe my first model or just say average average right and then just click submit right so once you submit right it's going to run your submission with the correct answer. It's going to take a little bit time. And then you get score, right? So the score here, the score that I use is the MAE, mean absolute error. It's basically option one. I show you, right? I use option one for evaluation, but you will use other options for this. Yeah. So basically, just take the difference and you take the absolute, and you take the average. So my submission have this, and after you submit, you can select, right? You can select up to 2 submissions for final submission. Because when you submit, if you go to the leaderboard, right, it's going to show you. So there will be public leaderboard and private leaderboard. Basically, your test data, 50% of the test data will be in public, and 80% of the data will be. So the score that you see is the public score. You will see the private score until after the data. And your aim would be to get the smallest score because it's the error, right? It's called the error. So you want the smallest error. So the less error you have, the score you get for this assignment. You only see the public score, so you can submit many attempts, and then you can maybe pick the top public score or pick the maybe something in between. Because if you try to optimize your model for the public, it might overfit, right? And in the private, it might not perform. So there are many cases in the past. Like for example, I have this population from last year. So in the leaderboard, right, you have some score, right, from public, right? For example, this person has 0.82, and then in private, actually go down to 0.7. So sometimes if you overfit the data, you may not perform well in the private. And for the submission, you can submit 10 times per day, maximum of 10 times per day. It's going to tell you the preset. This is when you can submit. So you have to plan. Right? If you submit on the last day, you only have 10 chances. That's the maximum you can submit. If you want to submit more, you have to submit the day before or the day before. So maybe you can submit 10 times a day or every day until the end, so you get 140 submissions. And then you can pick the tool that you use for the private leaderboard. Okay. So for the leaderboard, the public, you can also see other people. So you may ask them what they do if they have a report. But do not copy report, do not see. I think you can also create notebook inside here. Because I'm in the host mode, I cannot create a notebook, but I think you can create a notebook like when you submit. You can submit a notebook. You can create notebook. Here is basically the Jupyter notebook for this, and then you can just download. You can type the code here. You can run the model, the notebook on the website, or you can just use Google Colab. Or maybe you have Jupyter notebook installed on the computer. You can use that. So you can use any editor, any tool you want. If you create the notebook here, you can submit the notebook. It's going to generate the submission file for you. If you use Google Colab, then you are going to have to export a CSV file, and then you put the CSV file to the computation. Any questions so far? So if you rank one, the middle one, you are trying to get this. Then it's probably has the performance. So, so you have to pick, right? You have to pick, so you have to franchise again. The one with the dev have to store, and then another one will be the work of the store, and we will not overfit the data, and then some revenue. So that it depends on your strategy. Okay, and for this one, right, this one, can I add input? Configuration that is right. Oh, no. I see. So this notebook is actually for the Kaggle example. It's not, it's not just for this assignment. So let's go to the code for today. It's going to be, we only have one method. Very straightforward. Yeah, that's part of it. So today we're able to do the list, right? And the data, well, we just download the data. So we can just do that. So then so first of all, I have to mount the line. If you don't want to mount your line, then you can just upload the file. So I download my frame data set. I can just drop it here. If you drop it here, that is outside your notebook. When you close this folder, the file will disappear. So that is something that you have to worry about. So I have this kind of CSV. So I'm going to load the training data. So let me use my hand. Okay. For the training data, so I can import. So we can use pandas as always. So the path, we can just copy path from here. And CSV. And then you can say train data equal to cd.with CSV. Then, right? And if you run this dot code, now you already load the data. And when you want to do the linear regression, right? So we can do perform linear regression of the training data. We can use the linear model from scalar. So scalar.linear model import linear regression. Right? And then we can say model equal to linear regression. And then when you fit the model, you need to have the feature and the target. Right now, both feature and target, right? Both feature and target are the same, in the same variable. So we have to split X and Y basically, right? So we have to split the data first, right? So X, so we can train data drop. So which column that we want to drop, right? So we drop the last column, which is the U column. Right? This one is not feature, it's the target. So we drop U, right? And also we have to drop the ID as well, right? The ID as well. So we drop U, and then we drop the ID, right? And then Y equal to where data and only use U. Okay, so far so good. So we have X and Y, right? So we have our X. Let me X dot here just to show the X. So X now only have column that we want to use for linear regression. Okay, so we come back here. We want to fit the model, right? So we say model dot fit, right? Model dot fit X train and then X and then Y train. Right? We shouldn't have X and Y, so we see just X. Right? And then I can show the coefficient. Right? So I can say print model coefficient of coefficient and then that is. So the model will have the coefficient for each of the column, and we have the intercept basically to be right. So this one is like our A, is like A, B, and then this one is B, right? In the linear model. So if we fit, we take a little bit of time, and then you get this coefficient and then the intercept. And so you already have your model, or you have your model. So these are the parameters that you get. Now in the regression package, if you serve in the scalar, there are some of the parameter that you can use. Um, right. For example, you can specify that if you want to fit the intercept as well. So sometimes you want it to pass to the origin line, meaning that the intercept is always 0. You just set this equal to 4. Otherwise, you calculate the intercept. And another one is positive. The positive will force every coefficient to be positive. So what we have right now, we have some positive coefficient and some negative. So if you force it, then all of them will be positive. Right? So it's up to you. And once you have the model, right, you can save the model. It's important to save the model so you can load it later. So if you want to save the model, normally you will use the Pico library, and it's going to dump the model object to the file name model.pk. So this will save all the variables into a file. It's going to appear here, model.pk line. If you open it, it's going to be like gibberish. What is the binary data? But it will have your intercept and then everything else, right? So you can save this model. Basically, you will save all this coefficient and intercept, but in form of the model. So in the future, you can load the model. So you don't have to take it again. So you can load the model. Okay? Just use pico.load. And then you say open. And then you have the file name. And then you equal to. So you get the model back. You get the model back. This one, I have to get the correct path, right, after the model to be able to load it. Invalid node key. So basically, it doesn't find. Okay. Yeah, so you save and then you can load. So it's important that like after you finish one round, you save the model, and then you can use this file for it. So now that you have the model, you want to submit, right? You want to submit the answer. So you would have to upload the test data. So you upload the test data here. Right? So you load the test data, you run the model, test data, and then you save the result. So I load test data. So you can say have equal to test.cd here. And then I can load the test data. So I can say test data equal to pd.read CSV. And in the test, right, basically the ID is the one that we want to keep, right? We want to keep. So we can set index of the data to ID column, right? And if we test data dot set index ID in place equal to true, and then we can show you the test data dot get, right? Because if you just load it, the first line is going to be index one, right? And if you drop the ID, then there's no way to get ID. So you set this index. What you get is that it's going to start with the ID, right? So the first line is going to be the line 15,000, right? And then the rest is going to be your training data or your test data. Okay, and then I can make prediction, right, for the test data using the model. To make a prediction, so we can say prediction equal to model.predict, and then you put in the test data. And then you can add a column. Okay, so you can say test data new equal to the prediction. And then you can say test dot just to display it. So you have your test data, and then on the last column you have your prediction. And when you want to submit here, right, you need two columns, right? You need the CSV of two columns, which is ID and U, right? So I want to save the submission file using ID and U. Right? So we can say test data and only say U, and we say dot to CSV. Right? So if you save it like this, your submission of CSV is going to have ID. And so you specify the column that you want to save, and when you save to the CSV file, the ID is going to come in together. And you can download this. You can download the submission. And you go to the assignment, and you can submit your submission on CSV. And so I can say that this is maybe the default linear regression for SQL from scikit-learn. And then I can submit. So if I put the average score, I get this public score. So let's see if I use the linear regression, I will get smaller score, so it's better. And you can select both. Right? You can select both. So your comment will be appear here. So you know like which submission corresponds to what if you type the comment with the submission. Yeah, because I'm default, my result will not show the leaderboard. But if you submit now, if you join, or if you already joined and you submit now, it will appear here. So you have about 15 more days or 2 weeks to finish this assignment. Right. So yeah, I just use the base model. Right? Use the base model. Basically, you would have to check each column if it have the linear relationship between this column and the final column. So you can actually plot, right? Basically, you can plot, let's say, honeybee against you, right? And if you plot the honeybee against you, you have something like this, right? So the honeybee, mostly the data is on this side. So the honeybee is actually doesn't have the linear relationship, right, between the honeybee and the bee. So you wouldn't want to use honeybee. So you can do this for water as well. Let's say moss here. Right? Let's say we use moss here. And then you get something like this. Right? So it's going to be your call, whether or not this is linear. Can you share the yours here? Maybe take a square or something like that to make it look more linear. So you have to investigate a little bit of the data. Maybe here show what this is on this slide. Right. So a lot of the data here, you can see there are maybe repeated values. The one that are cover the real value is here, like the full set of footprint. This one actually have the better value. Right? For example, we use foot mass. So this one look more linear. It's going to be have the line around here, right? So maybe this might be good for linear regression. Right? But you still have like these two outliers, so you can remove them if you can find what they are. Right? So there are many more ways that you can get to this using just linear regression. Basically, you just have to play around with the features. So any questions for the excitement? So we have 2 weeks. So if you have any questions, I will see you again on 22. There's no class this week. I'm off now. So we will meet again on the 22. Okay. And I think I have finished the recording here. The recording will be uploaded later.